Log on, tune in, find out. Another good idea from Cambridge.
Practical, right?
Not at all.
Okay, so they printed a different title here, too bad. So Val Fedorov will talk about mixed effects models, design of clinical studies, the theory. Design of experiments. Okay.
Same thing.
Minor correction. I'm just waiting when we finish to read this first. Okay, I'm really very honored to be invited here. Thank you, Basha. Thank you, Sergey. But, of course, I thank more Basha because Sergey, when he invited me, he was still in my group. So
You turn it on, please.
Oh, it's good that it's not recorded. And somehow I feel a little bit strange because everyone talked about mixed models, and is it the third day or second day we're talking? Yeah, and the story is so long, so and I felt especially actually humiliated when I opened my old files and found this survey paper. It's not actually a survey paper by Johnson. It's some kind of collection of papers on mixed effect models, or in older times it's called stochastic parameter models, but it's more or less the same stuff. And you can pay attention how many pages in these two papers about stochastic parameter regression. So it's in the first one, do subtraction as well yourself, otherwise I'm afraid to be wrong. So, and okay, then next morning I moved from my office, and so I have to start to look for all the books, and I come across with Demidenko's book, and this book was frustratingly thick, and so about 500 pages, but also it's even worse. So I thought, what can I really talk about? And then I decided really to look through what people did actually in this area, and there are a lot of nice results, and probably some of them are going back to Ronald Fisher, and I'm sure that guys from United Kingdom can really provide a better information when he first published a paper about really random effect model. So, but I think it was before the Second World War. So the story is quite substantial here, and you find out, not all of you, but at least some of you who read the Rouse paper, wrong button. Oh, it's another way. No. Sorry. Some way. Oh, finally. So, and you find out that most of formulas which I will show actually can be found in Rouse paper. I think it's Berkeley Symposium. It was two papers, one in Biometric and another in Berkeley Symposium. So, but most of them were already there. I already will a little bit transform them to make them suitable for what we call optimal experimental design. Otherwise, it is very old stuff, slightly refurbished. And if you start to read for what is on this slide, you probably find out a lot of familiar names, and some of the authors are still sitting around, or are still around and sitting here. So, and yeah, friends, you are here as well. So, who else? Vlad Dragalin is here. So it's a lot of people actually right here. And I have to admit that a number of formulas which again wrong button, probably I never have used this. So, and a number of results in optimal design theory actually were also known for quite a bit, and it's basically was developed by Pilz, Jürgen Pilz, I think. I'm not sure. So he was in East Germany at that time. Jürgen. Okay, so, and he published a nice book, so I have a reference for edition 1991. Actually, the book was published somewhere in 80s. And let's proceed. So now probably you can understand why I play this picture. It's about recycling, and I think I somewhere again it's I somewhere sitting on this corner. I think it's remind me trying to understand what I am going to talk about. And let us start. So actually I try to be on the simpler side of this problem. And actually I do not understand why all this problem called mixed effect model. So where mixed coming from? So in all the times I thought that mixing here coming that you, for instance, you mixed binomial with gamma or normal distribution, which original observation, you mix with normal or whatever. Poisson, you mix, binomial you mix with beta, Poisson you mix with gamma. So that's why I thought where mixing is coming for. Then reading Jean books and other books, I understood that they actually talk about mixing of fixed effects and random effects. So whatever. You can accept any definition of mixed effect models, but I prefer actually the first one because it's really mixing. You're mixing patients from, say, distribution, say, Bernoulli distribution, binary distribution with beta distribution. Okay, so, and let us start with, I try to classify a little bit because I'm trying to understand myself what I am doing. And so, and there is model, I called model one, it's what you know, everyone uses. So you have observation y sub I, and it's vector, so it could be plenty of observations, actually, so, and nothing special. So you know how it's distributed, and you have to probably to estimate those parameters. Those parameters theta, and as soon as you decided to estimate this theta, everything is simple. You run maximum likelihood, method of moments, whatever you wish. Now, model 2, you have some kind of hidden parameters here, actually, theta sub y. So you have distribution of your observation. You believe that it's distributed like that. And this distribution depends upon parameter theta sub I. And I, it could be patient, for instance. Probably about 50 patients, potential patients here, but so, and each of you have this subscript. Chi, of course, has a subscript number 1. So, and you have some subscripts. But what you know, actually what you know is that this nice sample of patients was picked up from some population. Say, this population can be defined in this particular case as statisticians. So, and imagine you're just sampled. So, and actually, before I start to do some, the problem is that I cannot, or I am not allowed, to measure these parameters theta I directly. I just do not know them exactly. I can do some kind of measurement or estimations of them, but I do not know them exactly. So once more, it's my approach to the whole problem. There is a population, then there is some item, or patient, item somehow more neutral. There is an item which is picked up from this population. And as soon as I picked up this item, it's not random. I'm not Bayesian. I do not say so. There is a parameter theta, your height, and then I say, let us assume that it is random. No, it's not random. It's just your height, period. So, but obviously you are sampled from some population. Now, the same, both models could be formulated and very often formulated in terms of moments. That's what Eugene likes, and he advocated very much yesterday about that moment estimators and all these moments are much easier to handle. Of course, you can transform both of these models in terms of, say, first and second moments, and then play with them, and running instead of maximum likelihood, you can run least squares or something similar. And you just have to use these nice formulas, which you have to learn probably during statistics 001 or 1000 or whatever, so it should be there. No, so far, nothing Bayesian, by the way. Now, and there is two types. Let's once more look at that a little bit more attentively. So what we have here, actually, so I introduce dependence upon x, some covariates or variables, only at the second line. Doesn't work in my case. So do we have...
There's an easier one over there.
It's not easy, it's lighter. So actually I like this more. So x appears here. It works.
Push the right button.
Okay, so but sometimes you see slides. Okay, thank you. Good. Keep it. So, and dependence upon covariates appears only at the first line, or second. So the major line is here. So there's no dependence upon x. So population, as I do not introduce any covariates in population. So I generate parameters, and then I generate here dependence upon x. For instance, if we consider something in some regression model, we have xi theta theta I right here, and your y I equal something like that. So I introduce some dependence upon x at the second stage. I selected parameters, and then I introduce dependence upon x. For instance, it could be this PK model. So for each individual, we have his or her own dependence. There is another opportunity, actually, which is mathematically simpler, but I'm not sure that it's really more useful in practice, but sometimes it's useful. And I can introduce dependence upon x. I call it type 2 mixing. I can introduce dependence upon x in population. So I believe that, say, average curve there is already in population, and the rest is mixing from this curve. So it's different mathematically. Unfortunately, it's much more complicated here to introduce correlation between different observations, and we will talk a little bit later about this. But mathematically, it's much simpler because, for instance, if I have here gamma population, and this is Poisson, then it's easy thing to mix Poisson with gamma. I can get everything in closed form. No integration, no MCMC, nothing. So it's easier. Unfortunately, I cannot be proud that I use Winbox or something, but nevertheless, it's much easier from mathematical point of view. So two types. But because everyone talked about the first type, so I continue to talk about the first type of problem. And actually we consider two, and I think it should be emphasized that there is two problems. The first one, there is a population, and I do not know, or in this case I know quite a bit about this population, but let's assume I do not know too much about this population. So my first objective is to learn about population. To learn about population. And I want to emphasize that I do not follow the steps of Douglas and Jean. So I'm not interested in very much in variance-covariance structure, because all these linear models which you considered mainly, so it's because you are interested in special structure of variance-covariance matrix, or you introduce some structure of variance-covariance, and somehow dependence upon covariance coming like additional stuff. So that's why you mixed fixed effects and random effects in this way. I'm interested in population. That's the first step. Now, let's assume that I know population quite well. And in this particular case, I know population quite well. And then I picked up an individual, an item, and I have to design then, or to organize experiment to learn as much as possible and as fast as possible about this individual. So it's two different problems. To design experiment to learn something about population and to learn something about particular item. So that's why I try to separate these two problems. And I do not have too many pictures. I cannot compete with you. But nevertheless, because I didn't have any pictures the day before yesterday, I asked Sergey to help me with a few pictures. And this is rather simple pictures. So what we have a population. This is these blue points. And red cross correspond to expectation, to mean of this population. Now let's assume that these blue points are already sampled. It's who are sitting here. I don't remember. It's maybe 20 of them or 15 of them. Those who are too boring can start to count them. So, and afterwards, what we have done, what I asked Sergey to do, from each point, actually, I assume that I measure this point somehow. I measure this point, and I measure it with some error. And this error of the same magnitude as the scattering within population. Otherwise, the problem is not interesting, if one dominates another. So I measure them. And these lines, they connect true value, which I do not know, and measurement. So just to follow how everything is done. And then I just hide all these blue points, and then I have this one. So that's why sometimes this problem can be called problem with hidden parameters. So I just measure these parameters in some way, and I get these points. Say in this PK modeling, for instance, how we measure these parameters. We have two parameters, then for each individual, we try to feed our curve to observation in time, and we have, say, two estimates, so elimination and absorption. That's how we measure. And what is interesting, we already know the precision of this estimate. So actually I can draw some kind of circle. So it's precision of estimate. So I know these points, and actually to some extent I had to draw some circles just to emphasize it with some precision. But at that point Sergey told me that no, we have to go to play tennis. So now, next plot. And you understand the first problem. So first problem, so having these points, I have to find out this red cross. So, and from the first glance, actually I can do it very easily. I have to make averaging of these observations. And actually it will be a very good estimate. Very good estimate, unbiased. And in most cases I recommend to, and you will see that it's optimal estimator in many cases. And I recommend it to use this estimator as often as possible. Because actually what you are interested in, you are not really interested in that, because for your particular problem you have this. So work with this. It's your model. Because I do not believe that they're in hidden parameters. They try to sometimes evaluate structure of model, but do not help too much for estimation. Now, this is the first problem. Now, to the second problem. Now, we failed to draw ellipsoids or normal distribution here, so it's just selection of probably 100 points from normal distribution. So it correlated a little bit, but its blue points are identical on all these three plots. It's just the same points. It's just to give you image of population. That's what I'm trying to do with these blue points. So here there is still this red cross, it's mean. And now what I am doing, I have a patient, it's this green one, it's sampled. And then I made some measurements with this patient, and it's here. So how to estimate this patient? So what to use? So if you are naive statisticians who never read mixed effect models and never touched Demidenko's book, so I say, okay, I will use this estimator. Well, I observed it, so, and it's my patient, so I don't care about this crowd. No? It's just my patient. No, it's okay. So, but if you start to read books, they say, okay, we have to use information about our population. Or let us be Bayesians. I know prior information, and let us build some estimator. Better, because I know so much, so I have to do something better. And if you started to do all this nice theory, you find out that actually shrunk estimate, it will be on straight line connecting these 2 points. And actually, in my case, it should be even more or less in the middle, because both errors, both standard deviations are the same. And you can see that actually I have a worse prediction in this particular allocation of points. I have a worse prediction than trivial, say, mean, arithmetic mean. Now, what we can do, how to select? Is it really good, all these shrunken estimators? Let's consider another picture. It's the same samples, the same population, but sample slightly different. So here there is my patient, and my observation is here. In this particular case, shrunken estimate is better. So, and what I am going to do in the next few slides, to somehow to compare this shrunken estimator and this primitive estimator, which we can call arithmetic mean. When to use shrunken, when to use individual estimator. And then how to proceed with design. Gosh, time is running. Okay, but before to do this, I have to make some 5 minutes introduction to optimal design theory. And that is the responsibility of a chair just to stop me in 5 minutes with optimal design, okay? So what we are doing in optimal design, we have to define few things, clearly defined. So response, more or less it's clear. We measure concentration at different points. Concentration in blood, for instance, at different points. So it's vector. We know that it will be distributed differently. So, and distribution will depend upon X. It's control, what I call. Control, it could be doses, or moments when we do. So X is vector. It could be even some function. So it's not just X like it's one covariate. It could be any object. For instance, when you do chemical reactor, it could be temperature profile. So it's more complex. Theta are unknown parameters. And there are some variables which we can call uncontrolled, which are beyond of our control. So time is running and we became mature. It's a good news. Bad news is there is no way to avoid it, maturity. So it's running. So now, then we have to introduce what I call utility. Not only me, but not only I, other people. So utility, it's what we really want to get from our experiment. Usually it's unknown parameters. Sometimes it could be temperature profile, whatever you need. Then we have to introduce cost, because we have to pay for everything, and it should be done in advance. We have to understand what we have to pay for. And of course, I have to understand how control can be changed. So it's general setting in optimal design theory. Now, I suspect that a lot of people from this audience have seen similar pictures many times. So I skip this one, so it's maximum likelihood estimator. What is important for me is that there is some asymptotical results. I emphasize asymptotical results, that variance-covariance metrics of our estimators related to so-called information metrics. And this information metrics depends upon what I call design, and design is nothing else but allocation of my design points and how many observations I perform, here's the definition, perform at this particular point with subscript I, or for this particular individual with subscript I. And then I introduce cost, and cost, how I introduce? Cost is defined by, say, by X. It also could be defined by not only by X, but time, for instance, for how long. Sometimes you do not control time, but you can stop sometimes. So there are things which you can define. So this is cost, and it may depend potentially upon unknown parameters. And again, cost, easy to find out when you do introduce optimal design. Now, what is the most important for the whole design theory, at least in its current existence? That information is an additive function of information which we can get from each particular experimental unit. That is important. So if we define experimental unit, then information matrix is a sum of information matrices. That is important. Now, and this information matrix actually have a few very simple explanations. First of all, it's nothing else as an average second derivative of likelihood function in the vicinity of true value or maximum of this. Depends how you define, slightly different. Or it can be considered as a variance. I talk about log of likelihood. So, or it's just a variance of first derivative at the vicinity of optimum. So it's not, you see, it could be connected with numerical technique. It's just function, and you look at maximum of this function. So it's actually all based on just Taylor expansion up to the orders 2. Period. Nothing else behind all that. And all asymptotically somewhere for huge n, it's really important metrics. But because we do not have anything better, we have to play with that. Here there are some formulae about transformation. So most of you knew this. If you move from one set of parameters to another set of parameters. Now, and what is experimental design? Now that is simple now. Notations are fancy, but it's simple. I mean, they are not very fancy, but I like this xi and psi, they look nice. And, so and what we have to do, we have some kind of criterion of optimality. It's some function of information matrix, because we cannot play with information matrix too much. It's multivariate object. So we have to reduce it to scalar. And then I have constraints on cost. So n observation, and I have, this is normalized cost. And so when I normalize cost, I have to multiply by n capital, total number of experimental units. And this cost should be less than, say, C capital. And if you do some exercises, then you can find out that this optimization problem is equivalent to that optimization problem. So you have to actually minimize some functional of information matrix standardized by losses, by cost. In all the times it was standardized by number of observations. And so in this case, phi actually was 1. And in all the times, nobody cared about cost. You see, economics was much better. So, people just cared about number of observations. And so, but it's mathematically more or less the same. Now, as soon as we formulate it, then we can be a little bit more sophisticated or whatever, convoluted, and we can talk about Bayesian approach, for instance. And if we have some prior information or prior observation, then your design problem changing slightly, because then I have to add information, prior information, which is described by information matrix of this prior knowledge, with knowledge which I potentially can accumulate, or will be able to accumulate. And again, I have constraints of on cost, which really related only to the second term. And again, after some arithmetic, I can show that it's simple optimization. Design, yeah, I'm done. So it's relatively simple. So, and what I want to say is that actually machinery for that is well developed. Now, it's not about design, it's about Eugene. Now, yesterday Eugene said, why people so obsessed with d-optimality? Was it you, Eugene? No? Who it was? Oh, it was you, okay. So, Eugene defended d-optimality. But actually, from here you find out a few relationships which describe why we have to use d-optimality and what is called, I called lambda optimal. I don't want to, when you minimize the worst eigenvalue. So because all other criteria, reasonable criteria, is actually between these two. So d-optimality actually to some extent optimize the low bound for most of reasonable criteria, and criteria which is based on eigenvalues of information matrix or D matrix minimize the upper bound. And here everyone can, okay, those who knows equivalence theorem, Kiefer-Wolfowitz theorem, it's actually here. Only we have some generalized version. Instead of, say, one observation, we have mu. It could be matrix because, say, in some particular cases, say, in PK modeling, our item contains, for instance, 10 observations. So, and this matrix mu can be higher order than rank 1. So higher rank than rank 1, because you have, say, 10 observations on one individual. So that's why it's important to introduce slightly generalized version. And here there are generalized version for when we have some cost. Here there is generalized version when we have some prior information. And as soon, what you really to do, that's the most important thing. You have to derive information matrix of a single observation. Observation, when I say observation, it's more general. It's observation on you. So PK profile, your PK profile. So that is observation. And then everything is relatively well elaborated, and it was elaborated for other criteria. Is Anthony here? Oh, sorry to wake you up. I'm sorry. So actually this table is copied, I did it intentional, from our paper. You can find out also some kind of sensitivity functions and all machinery which is needed for criteria which are different from d-optimality in this old paper. Was it 88? So
Yes, there's an error somewhere. There's something.
well, come on, man. Anthony, nobody can read it. So, and afterwards you see, I put my last picture here. So after that, the process is very routine. So there are tons of software, they called monoliths. Is it correct or no?
Yes, but it's not for design models, it's for estimation.
Oh, for estimation, sorry. What do you have for design?
PFIM.
Oh, PFIM.
We'll learn tomorrow a lot about
Oh,
and
okay.
yes.
Okay, so machinery is well developed. What I want to say is there is even some software in SAS, there is some software in JUMP, there is software in R, so it's not a big deal. And now mixed effect models. And I don't have too much time, but so I have to rush. So now let us formulate the program. And I will start with a very simple case, because if I do not understand something on this stage, then probably I will not understand later on. And that's my feeling. So I do not understand a lot of things for nonlinear models, and mainly because I do not really understand comprise completely what is going on with the linear models. That's my feeling. So, and I assume also that at this stage, variance-covariance matrix of my observations is known. Usually people say they're independent, but I just put V, as my name starts with V, so maybe because of that. Here there is sigma, it's variance-covariance matrix of your population, or prior knowledge, whatever. So, and then it's obvious that if I'm interested in the population, this simple formula works. It's nothing else as some kind of weighted average of individual observations, where theta with bar is just nothing else but least square estimator, say for NPK case model for unknown parameters. Period. So it's individual estimator. So if it's I just measure directly your weight, height, or whatever I2, it's just direct measurement, and that's all. So I have to find out estimator, individual estimator for each individual, and then to take average. And how it's average actually? Pay attention how it's average. So what I am doing, I add up two errors. One is variance-covariance matrix actually for individual observation, it's this one. And another is variance-covariance matrix for population. That's all. If sigma is big, so our precision is very high of our measurements, nobody cares. It's just take arithmetic mean without any weighting actually. So take arithmetic mean. If all our experiments are the same, it's also arithmetic mean, nothing else. Only when we have some kind of fancy different schemes, so we do PK analysis on one patient on one set of times and on another patient on another, then some kind of difficulties, not difficulties actually, more complicated arithmetic is needed. Now, this is about population. What about, and this best linear unbiased estimate? Good. And coincide in normal case with maximum likelihood estimate. Now, what about individuals? The first estimator is actually here. So this is individual estimator. And this conditional, condition on theta I, on I, is the best linear unbiased estimate. This is the best for you if you do not care about the crowd. Now, another estimator, when you actually care about the crowd, in which sense? So if you, this estimator theta with cap is also relatively good one. So what is good about this? This estimator, on average, I emphasize, on average, across the whole crowd is better than individual estimate. In which sense? So for each individual, this is actually biased estimator. But when you do averaging across all individuals, this biasness, which is due to this term, it's population parameter, it will disappear. So on average is better. But I emphasize the first estimator conditioned that it's U is better than this one because we do not have bias term and it's actually best linear unbiased estimator. So what to use when a patient comes to you, you have to decide. If you are a doctor, you probably say, okay, I probably have to use the second one. Because if I will do something with the whole crowd, which will come to me, so probably on average, I will provide a better advice, better prediction what to do with these patients. But if it's, I care about myself, if I came to you, then probably say, oh, let's still use the first one. Because in my particular case, it's more assurance that it will work better because it's unbiased, and unbiasedness is probably important in your particular case. It could be slightly larger total deviation, but at least it's unbiased. Yeah, I will please, because otherwise it will be too boring.
No, it's sometimes also you don't have enough individual information so that you could get this theta I bar. Sometimes you cannot inverse.
Yeah, exactly. I try to
only get theta at.
Yeah, that's exactly what. When you do not have enough, but about I called it singular cases. For instance, if you have two observations on individual and you have to restore the whole PK profile, you have nothing better to do than to say, I know better. And you use either they called Bayesian approach, when they take this beta from blue or sky, I don't know.
But it's exactly the second formula.
Yeah, it's exactly. But you see here, it's actually you have to use this one if you are in real life, because you can show that maximum likelihood estimator should be this. Theta with cap, theta true should be replaced with theta with cap, which is defined here. So pay attention that how this estimator is built. You have information from your patient and you add up information, it's sigma minus 1, from population. So, and it's good if it's real information. If it's not, how they call subjective information solicited from key opinion leaders. So, now, everything so far was simple, and to show you that I still can write some formula or copy some formula from some papers, because it's easy now to do with all these PDF files. Actually, you can do more complicated problems, and now you can pay more attention to variance-covariance structure of population, because in many cases, variance-covariance structure of population can contain, of course, unknown parameters. Sometimes it's matrix itself, sometimes this matrix parameterized, and in particular case of random effect models, models with random coefficients, it could be this one, this matrix S, which is variance-covariance matrix of population, of our final observations is of this structure. And by the way, this structure is good. And information matrix from this structure you can derive. So probably tomorrow you will talk for 3 hours about this, only replacing f of x by derivative of response. And this is when you have actually singular cases, so it's general formula. As soon as you have enough observations on one item, individual, then formula is getting trivial. So your information matrix for a single observation is nothing else but m minus 1 information matrix for one individual plus sigma. These two formulas are equivalent. Do arithmetic multiplications in algebra matrix and you will get. And as soon as you build this function or information matrix of single observation, you have to go to, do you remember this nice slide with these wheels? Go there. You are done. Now we talked that information matrix was built for when you work for population, when you want to design experiment for the whole population, when you are interested in parameters of population. Now, when you are interested in particular individual, everything is trivial. So, I mean, not trivial, but it's simpler. Because if I'm interested only particular in myself, then there is nothing new in experimental design here. You have to build experimental design which for ages, I can say for ages, but at least for
decades.
No, half a century. So it's still 5 decades, but so it's no. So nothing new here. So when you have one individual, don't be too sophisticated, just do optimal design for this particular individual, period. It's another thing we have to remember that very often you cannot make too many observations on one individual. So don't apply asymptotic theory for one individual. I mean, this continuous design. Because if you have 5 observations on one individual, say 5 times, don't. Of course, if it's PhD student, you can do this, but in practice, you just can't do optimization in for 5 points. Now, it's a little bit more complicated if you want prediction based on average. Then design should be a little bit different. And if you look at that, it's actually design which corresponds. You have to really to handle the case when it's here. So you have to minimize this, but you have to handle situation when you, by the way, it should be changed, but here it's correct. So what you have to do optimization problem like you have some prior information. And this prior information is nothing else. You can imagine that one experiment is on you and another experiment is like on parameters directly, theta parameters directly. So what you are doing, you add up information from 2 experiments. And then it was, you probably remember, it was some couple of formulas for case when we have prior information. So machinery is also known. There are one thing which no, okay, so people are so quiet. I hope they will ask some nasty questions later on, because you can ask some. So there is the same machinery. I have a few minutes. So when we stop, Peter?
10 minutes.
10 minutes. Oh, good.
Including discussion.
Including
Okay,
discussion.
good.
So if you speak fast.
Well, we can discuss over there. Okay, so so far I assume that matrix V, so variance covariance, all variance covariance matrices are known. And of course it's idealization, it's almost never known. So then you have to do a little bit more complicated thing. Then you have to really to do design, assuming that you actually estimate not only parameter theta, say, of your PK model, but you have to estimate also parameters which enter sigma matrix, which describe your population, and actually in this particular case, these of simple form, and also parameters of variance-covariance matrix of observations on particular individual. Then, after some arithmetic, say for random effect models, you can show that this matrix of single observations will be of this structure, which is rather boring, described here. Do f of x is derivative of your response function. So it's this structure. What is good about this structure is that actually it's blockwise. You can see that in this particular setting, you can partition in its two blocks. One block is related to variances, and another block related to our response model. And therefore, we can apply here, or first of all, because it's blockwise, you can show that if you are interested only parameters which describe your, say, dose response, your optimal design will coincide with the optimal design for this model under assumption that everything is known. It's a very nice fact, very nice fact. So, and it's in this setting. But in more generally, unfortunately, it's not true. More generally, unfortunately, it's not true. Because if you have common parameters, both in response and in your variance-covariance function, then design will be a little bit more complicated. And actually, I like presentation in the terms, Eugene tried to do this yesterday. So when you do some kind of least squares, which contains one term which is residuals for your observations minus response, and another term which contains actually this squared term when you subtract from estimator of your some estimate of your variance, I mean variability minus variance. Good, thank you. And then you square that again, and in normal case you have to divide it by sigma to the power 4, a little bit more complicated. It's, by the way, in our paper with Sergey, and you are done. So it also can be reduced to least square, roughly speaking, to iterated least square. Summary. So when you are handling this, what I call mixed effect models, we have clear, and you try to design experiment, you have to clearly understand what is this mixed effect model is used for. Are you going to learn about population, or you are going to your doctor and you try to predict, I'm a medical doctor, all here almost doctors, but not medical. And so if you are really a doctor, so you probably have to somehow predict something for your patient. How you do, of course, doctors do not do experiments, but at least they do some analysis of data. But in general, if you want to really predict something for a patient, then it's completely different design. Simpler, but it's different. Now, it's very important to understand what is the definition of single observation, because people try to introduce some kind of multiplication of spaces of design, so one design of inside patient, another design across patient. So I think it's no sense really to do anything sophisticated about one patient, because it's relatively simple structure. You can select either 5 observation or 3 observation or 4 observation on one individual. And if you introduce cost, you can do quite well. And actually, if we go to, how to jump to the one of the first slides. So actually, most of efforts which people do in optimal design of this PK type of models, it's actually what we are trying to do. What is better? To have a lot of these points, blue points, or to have these intervals or segments shorter. That is the trade-off. And I think that in most cases, it's really better, of course, if these errors are not tremendous, it's better to have more these points. Sometimes it could be more expensive. But, because if you get this patient and say it's quite difficult, for instance, to hire, not to hire, but to attract patients to do some kind of trials on safety or toxicity, you pay money, big money, relatively big money. It's big for them, for these poor guys. They're small for big companies and so. But nevertheless, it's called. So that is a trade-off, basic trade-off which you do in this design for mixed effect models when you try to learn about population. Either segments short or a lot of points. And now, is it special point here? Up. Now, as soon as you define what is a single observation, derive information matrix. Good luck. So it's usually not that simple. And you can spend the whole days and discussing it. And come to this nice place that is even more interesting. And then it's good to understand what you are paying for. How much you pay for patient, how much you pay per analysis, how much you pay for delays, all that stuff, what kind of logistic you face, so it's important. Then boring computing, and then I have to say I never used optimal design in practice, never, because it's only for benchmarking. You see, you have to use some more practical design and compare them, benchmark it to optimal design. Because there are a lot of things which you just cannot take into account when you do your computing. But when you have some design which is, from your point of view, is close to optimal, looks good from, say, logistic point of view, because a lot of designs, say, when you do the sequential design, like in your example, it's great mathematically, but logistically it's a nightmare. So, and if you can replace this design with, say, three-stage design, which lead to losses about 10% in number of patients, who cares? Because you save immensely more on logistic. So just common sense. So I think that all this work is needed, but we have clearly understand that it's benchmarking. We, roughly speaking, we put a target, which practically never can be approached, but we have to be as close as possible, taking into account various practical aspects. But then, it's not for academia, because you still need to nurse or whatever word a lot of students, and they have to really to do exact good mathematical results. Thank you.
Thank you. Any comments, questions?
I can see one. Basi-
Yes, it's about benchmarking, the last comment you've made. I think it may be perhaps possible in some cases to add some restrictions to your optimization problem. If you have a mathematically defined criterion of optimality, and then if you discuss practical issues with clinicians, could you then add them as restrictions into the optimization? And then instead of having this fantastic optimum design and then sort of rounding it for practical purposes, maybe include these purposes in the optimization first of all.
Yeah, I agree. So mathematically it's possible, but from from my experience, the following happens. More restriction you add, so roughly speaking, flatter your utility function is getting, utility in the sense. And then you, for instance, good example, when you try to build this, what they call average design, Henry calls them pseudo-Bayesian design, when they try to, instead of optimizing, say, minimizing determinant of variance covariance matrix. You try to minimize average value. So when you optimize it for one parameter determinant, then it will be just 5 points, whatever, number of unknown parameters. When you do this averaging, then designs with 20 points will appear. Mathematically, it's nice. But you could not, you see, introduce, as soon as you see this fact, you say, oh, I have to introduce another constraint, number of support points. And this is infinite work, so that's why I propose, it should be some kind of common sense. So first, it should be optimization problem which you can handle relatively fast, because then you can run a lot of scenarios, first of all. And the second, when it's simple, then you can explain it to your customer. And then customer can himself show, okay, so customer can define what is really suitable for or not suitable. And then you can just say, okay, let's use this design and this design close to this idealized situation. Then we are happy. That's my feeling, okay. Oh, sorry, it's Peter should do this.
You were assuming a criteria that would target good estimation of all the parameters, including the variance parameters. But wouldn't there be a context where you would only be interested in the theta parameters? Say?
Yeah, that's what I said at some point. You remember I said the matrix, yeah, there are such situations when you are interested only in parameters. It's here. If you are interested only in parameter theta, dose response, for instance, behavior, then actually you can do, in some situation, nice partitioning and build so-called DS optimality. You have to remember, Bill. It seems to me at some point you built yourself this DS optimality design. Don't remember? These are
Well, just a small technical point. When you this V is really the conditional variance of
Correct.
given theta.
correct.
So that could, in a spatial situation, depend on the design. Have you any idea, which would really, it's that conditional independence of the, if you like, the error part from the parameter part that you use here. I mean, when V is actually design dependent, like in the correlation case, have you got any suggestions?
It's actually everything stays the same. You see, because when you introduce information matrix, it's not only design dependent, it depends. You see, in my case, X, this bold X, to some sense it's individual design for, say, particular day or something. It's easy for me to explain on PK case. Sorry, friends, to use, to pick up on PK modeling. Because it could be, for instance, 5 times when they take a sample. And then it will be matrix 5 by 5. If they have 2, it will be 2 by 2.
Except that you could have an autocorrelation parameter in there as well, which also needs to be estimated.
Yeah, it could be a correlation parameter, because if you actually, they assume that blood sample, so observations of blood samples are independent. And it's not for one individual. If you repeat 2 times the same, it's simplification. And in special designs, I don't know what kind of special designs you are talking about, but it could be completely different correlation matrix as well, because if you talk about, you see, allocation of meteorological stations, it's more or less stable, but you can make measurement every hour or something, and so then you change.
Well, anywhere where you've got a time series or a profile of an individual, you might have a
Yeah, and it doesn't matter. What matters if you accurately include it in this matrix, which I call mu. It should be accurately imputed there.
I think the coffee is getting cold. Can we just move more questions to the coffee break? So let's thank again Val for